Okay, so we're going to be starting a new topic on simultaneous equations and quadratics. And the first little chapter that we're going to look at is where we have one linear and one non-linear equation. Right? So a linear equation is just a straight line, and a non-linear function could be anything. It could be a hyperbola. We could have a quadratic, we could have a circle, etc. So any nonlinear function. Now, before we look at solving these simultaneous equations, we need to just remind ourselves the two methods that we use when we are solving for simultaneous equations. The first being elimination, where we try to make one of the variables in each of the equations the same, and then eliminate it through addition or subtraction. Or alternatively, where we solved for one variable and then substituted it into the alternative equation. And we need to know both methods efficiently and proficiently to continue. Okay, another important tool that we need to know in order to solve simultaneous equations, especially from now on, is going to be solving more complicated quadratic expressions, right, using the three different methods. Okay, so we can either factorize to find the solutions, we can complete the square, or we can use the quadratic formula. And the order should always be to try to factorize first, if we can, because it's the quickest and easiest. If we can't factorize because it's impossible to see the simple factors, we should complete the square, right? Especially if the coefficient in front of the x term, so the number in front of x is even, that will give us a nice, easy completed square. And finally, if all else fails, to use the quadratic formula, okay? And we should always use this method last because it is the most error-prone and the most time-consuming, right? So only use it if really desperate, right? Try to factorize first or complete the square, right? Completing the square it's always good practice. Okay, so let's look at a graphical interpretation of when we're solving simultaneous equations. So the first time we are introduced to simultaneous equations is where we are looking at them visually on a graph. So over here, we have the two equations, y equal to x plus 1, and we also have the parabola y equal to x squared plus 5, right? They've been drawn, and so visually we can see there are 2 points of intersection. Now the points of intersection, so the one over here and the one over here, these are what we call the solutions, okay? They are the values where these two equations exist at the same time, okay? And they will have an x value and they will have a y value, right? Both of them. Now, usually, right, when we solve these simultaneous equations, we will generally solve for x first, and then using either of the two equations, we would solve for the other variable. But the order doesn't matter, right? But if we are asked to find the solutions, we're asked to find both the x and the y solutions, unless otherwise stated. So if they only want the x solutions, they will specify only the x coordinates, etc. Okay? So let's look at solving these two algebraically, because that's the whole point of this topic. Okay, we could solve graphically, but we would need specialized graphing software because it's almost impossible for us to freehand a parabola accurate enough to get proper solutions. And so we need to know how to solve these things algebraically. Okay, so here we have our two equations. I'm just going to quickly correct. This is minus 5. Sorry. Okay, so here we have our two equations, and in the first one we have y equal to x plus 1, but we also have y equal to x squared minus 5, right? So if they are both equal to y, they both have to be equal to each other. So we have x plus 1 equal to x squared minus 5, and we're just going to rearrange and solve like we would for a normal quadratic equation. X squared minus x, and we're going to have minus 6 equal to 0. All right, quickly, the factors of 6 are 1 and 6 and 2 and 3. So we'll have x minus 3, x plus 2. So we want minus 3 plus 2 to give us negative 1 for the x equal to 0. So we have x equal to 3 or x equal to negative 2. So those are my two x coordinates, right? Now I also want the y solutions. And I have two choices here. I can either put the x coordinates into this equation or into this equation, and I should theoretically have to get the same solutions, okay? Because that's exactly what I'm after. So I would say just use the easiest of the two. The linear one's normally going to be easier. So if x is equal to 3, I can see that y is equal to 3 plus 1, so that's 4. And if x is equal to negative 2, then y is equal to negative 2 plus 1, which is negative 1. And it could also be useful to write your answer in coordinate form like this, with our x and corresponding y coordinates together. Okay, let's do a more complex example. Here I have a linear function again, and I also have some other function, okay? Now, it doesn't matter what the other function is. We're just asked to solve when these two functions exist at the same point in time, right? Now, we're going to have to not only substitute, but we're also going to have to manipulate one of the equations in order to solve. So, if I have 2x plus 2y equal to 7, I need to solve for one of my variables, okay, in order to substitute it into the next equation. So this is equation 1, and we can say this is equation number 2. Now, if I substitute something in place of x, I will have x squared. And if I substitute something in for y, I'll have y squared multiplied by 4. So I can see it's going to be easier to solve for x and substitute for x, because then I don't have to also deal with multiplying by 4. So I'm going to say from equation 1, we have 2x plus 2y equal to 7. I'm going to solve for x. So I'm going to move everything that's not x to the other side and divide through by 2 to solve for x. And I'm going to rename this to equation number 3. So I'm going to no longer be using equation number 1. Right, what I'm going to do here is I'm going to substitute equation number 3 into equation number 2. So in place of x in equation number 2, I'm going to substitute my 7 minus 2y over 2. So here we have x squared. Well, let me write the equation first. It's x squared minus 4y squared equal to 8. And I'm going to replace x squared with this. 7 minus 2y over 2 squared minus 4y squared equal to 8. And now we're just going to solve. So we can expand at the top. We're going to get 49 minus 28y plus 4y squared all over 2 squared, which is 4, minus 4y squared equal to 8. I can eliminate that 4 on the denominator by multiplying the entire equation through by 4. So we'll get 49 minus 28y plus 4y squared minus 16y squared equal to 32. Right, now we're just going to group like terms and solve for y. So we'll get 12y squared plus 28y minus 17 equal to 0. Now, looking at this, it might seem like the easiest method to solve this would be to use the formula or to complete the square. However, if we have a look at this number here, negative 17, it's a prime number. Prime numbers only have two factors. We only have 17 and 1 to work with. And so we can consider the factors of 12, and we can think it's 6 and 1, or 12, or 6 and 2, 12 and 1, and think how can we use those to get 28. Well, if I take two lots of 17 and I subtract 6, I'm going to get 28. So I'm going to use 6y and 2y, and I have 1 and 17, so I said I wanted two lots of 17, and I want to take away one lot of 6, and that will give me 28. So something to consider when you're trying to factorize is if one of the two numbers is a prime number, then you know at least one set of the two factors. Okay, this is going to give me a solution of y equal to a half, or y equal to 17 over 6, right? Which is also just, negative 17 over 6, which is just negative 2 and 5/6, whichever answer you want. Right, from here we're going to substitute into one of our original equations and solve for x. So we can stick it into either equation 3 or equation 1, it doesn't matter, and we'll get x equal to 6 and 1/3, or x equal to 3, and we can write this neatly as a set of coordinates 3 and a half. Okay, so again, importantly, if we aren't specifically told to only give x coordinates, we solve for both coordinates, and we can simplify that or make it neat by writing them together as a set of coordinates.